Hello, in this lecture, we will summarize the basic of logic design in our that you have already learned in our course of architecture and networks. So saying about the basic of logic design, we have the computer will work with digital. Why it is digital? Because you use the voltage as the high or low voltage and so you have a binary number either 0 by low voltage or 1 by high voltage, and so the true in logically will be value of 1 or phase in logically will be the value of 0, and it refers as the 4 voltage level, and so it refers to as asserted signal or deserted signal. Assert is 1 and desert is 0. Values 0 and 1 are called the complement or inverse of one another. So inverse of 0 will be 1, inverse of 1 will be 0, or in other words, complement of 0 will be 1 and vice versa. And you have two types of logic blocks. The first one is the combinational logic. In the combinational logic, you will have various calculation by AND or and NOT, but the combinational logic will not contain any memory. So that please remember that the combinational logic has no memory, and so the outputs will depends only into the inputs. Another logic you have is the sequential logic, which has a memory inside, and so the outputs will depend not only into the input but also into the value stored in memory, which is called the state of the logic block. Next, we will go to the truth table. As we have talked before about combinational logic, that is the logic block that has no memory and it do some logic function. That function can be shown by truth table. You will have the inputs and the outputs for the truth table as showing here. For the inputs, you will list all the possible inputs and then you list the result or the output of the function. So as you can see here, I show you here the truth table for the NOT logic function, for the AND with 2 inputs logic function, for the OR with 2 inputs, and for the exclusive OR with 2 inputs. And for the NOT, it is a complement or the inverse. So input A with NOT A will be the inverse of A. For AND function, A and B will be 0 if either A or B are false, and it will be 1 when both of A and B are true. Only that case the output of A and B will be 1. The OR function, OR logic function, will have the value of 0 only if both A and B are 0, otherwise the output will be 1. And for exclusive OR, you have if A and B are the same value, it will generate the output of 0, and if A and B are different, the output will be 1. Among these, we have NOT, AND, and OR logic as the basic logic function or basic logic gate. Another way to express the logic function is using logic equation or Boolean algebra, so here for Boolean algebra, you can use either or and not with this sign, plus for or, point for and bar for not. And as I said before, the OR logic is a sum of A and B, and it will be 1 if either of the variables is 1. For the AND logic, it will be 1 only if both inputs are 1, and for the NOT value, it will be 1 if the input is 0. We can use the kernel maps to show our logic function or our truth table in order to make the minimization or optimization for our logic circuit. I think you still remember it from our labs. Here I will not say too much about Carnap maps, but I will go into an example here. For example, here you have a table with truth table with inputs of A, B, C, and with the outputs, 3 outputs D, E, F. Each of D, E, and F are a different function. And for example, if we look into output of D, we will show the kernel map for output D by the input A, B, and C. We will group input A and B together, and so 4 columns will be available here with the 4 possibility of A, B, that is 0, 0, 0, 1, 1, 1, and 1, 0. A rule here is in the for each column only 1 bit will be changed. So here 0, 0, and then you change B, you have 0, 1, and then you need to change A, and so you have 1, 1, and then you need to change B again for the final value, which will be 1, 0, and for the line you have the value of C. So it will be 0 here and 1 here, and then you for these inputs you will fill each of the element of this table by the output of D, and so here you can see only all value of 0 here will be 0, so this output is 0. Other elements of the table will be filled by 1, and that is a kernel map. And then you can use kernel map to optimize your function. The detail of how to optimize this function you can look again from our lab. And next we have the gates, which will be used to implement the logic function, and we can use 3 basic logic gates or basic logic function, NOT, AND, and OR, to implement all other basic logic function, all other logic function. And here AND, OR, and NOT are the 3 basic logic functions that we will use in our implementation of any digital device. For AND and OR gates, you will have multiple inputs, at least 2, and you can have 3 or 4, 5, but in real hardware you should have maximum 3 inputs for AND and OR gates, but in paper or in our exercise you can have multiple input AND and OR gates. For the logic function, you will have only 1 input for NOT function or inversion, and all of them will have only 1 output. Here is the how you express or how you show the AND, OR, and inverse gate. Here is the image of AND, image of OR, and image of inverter or NOT logic gates. And in simplicity, we can combine them together to make it simple. Here, for example, if you have a complex logic like this, not A or together with B and then inverse that value, instead of using so many not function, not gates as showing here, you will replace not gates by bubble. And so here you can see this image. It is it will show the same logic or the same gates with this with the above one, the NOT or the inverter are replaced by the bubble here. And so with that you will have the NAND gates. So here is the image of NAND gates, NOR gates, and here it is a NOR gate. And if we combine so another logic function that are often used in computer design, it is a decoder. You can use that three basic logic gates to combine them together to make the decoder. It is AND bit input logic. Here is an image of a decoder. With 1 bit input and 2 bit output, the function of a decoder is based on the input value. The decoder will choose one among the output and set it to 1. So for example, here if you have the input value here is 0, the output 0 will be set to 1. And if and the output 1 will be 0. And if the input value here is 1, output 0 will be 0, while the output 1 will be set to 1. So it is and after that this output will be used to select some part of the logic, some parts of other device or other logic, and that is why it's called decoder. Here is the truth table for the decoder. As I said before, it have only 1 bit input, and so it have two values, either 0 or 1. Two output 1 and output 2. If the input is 0, the output 0 will be 1, while the output 1 will be 0. And if the input is 1, the output will be output 1 will be 1, while the output 0 will be 0. Of course, you can increase the number of inputs. For example, you can have 3-bit inputs, and in that case you can have a decoder with 8 outputs, because with 3-bit input you have 8 keys or 8 values, and so you have 8 outputs corresponding with that input. An inverse of the decoder is called encoder. And for the encoder, it do the inverse thing. With the here is an 1-bit encoder. It will have 2 input, either 0 or 1. If the input 0 equal to 1, the encoder will make the output of 0. If the output 1 here is 1, the encoder will make the output value to be 1 to show that the output of the encoder will show which input are positive inputs or which input has the value of 1. All other inputs will have the value of 0. The next logic function that often be used is a multiplexer. It is one kind of basic logic function that often used. it works as a selector. Here is an example of a two input multiplexer. You will have two input A and B, and you have a selector here. If the selector is 0, value of A will be selected and it direct to output C. So C will equal to A if the selector is 0. And if the selector is 1, it will select B for the output, and so in that case input B will direct to C and get out, or in other words, C will equal to B if S is 1. And of course you can extend the multiplexer not only two inputs A and B, but you can have many inputs A, B, C, and so on until N, and you will have more than one bit or multiple N input multiplexer with more than one bit for selector, and depends on the value of selector, either A or B or C or something will be selected and directed to the output. In the inverse function, you will have the demultiplexer, or in short it will be demux. It is an inverse of a multiplexer. Here it will depends on the value of selector. Here demux will direct C or the input into either A or B, so that C will appear in A or in B, but not in the both at the same time. As before, we say about ALU, and now we will go in a little bit more detail about ALU, 1-bit ALU. We know that our ALU, we need to do the function for AND and OR, and so this logic or these gates show how we develop AND and OR 1-bit ALU. Here you can see it. We have AND gates and OR gates available here with the two inputs A and B, so that at the end here we will have A and B available here, and here A or B will be available here. This multiplexer use the operations as the selector. If the operation is 0, it will be the AND function, and so we select the output of AND logic here, so the result here will be A and B. If the operation is 1, it works as a OR logic function, and the result of A or B here will be directed to the final result here, and so this result equal to A or B. We will also have the adder in order to add two values of A and B together, and we have half adder, in which as we know before, when we add two bits together, we may get two 1 bits together. We can have the result of 1 bit and one more carry out, or the result might be 2 bits together, and so here we have a carry out and a sum with two input bits A and B. This logic is called half adder. We will not go into details of this, but we will go into this a full adder, in which the carry in will be taken also, which means carry in here will be the carry out of the previous adder, and that's why we have the full adder with 3 inputs A, B, and carry in, 2 outputs, one for the sum and the other for carry out. And carry out, here is the logic function for carry out, and this is the logic function for the sum. and of course we can connect many full adders together to make for example here 32 bits ALU. We connect 32 1 bit ALU together or one full adder together. The carry in get here, A and B get here, and so we have the sum available here and the carry out available here. That carry out will be the input carry in for the next for the next full adder together with A1 and B1, and three of them add together to generate the output result 1 here and the carry out 1 available here, and so on until the 31 full adder. If we connect them in sequence like that, we will have 32 bits input adder, and it generates 32 bits output together with a final carry out available here. And that way of that organization is called ripple carry. Next we will go to the sequential logic. As we said before, the sequential logic here we have two types of logic blocks. The combinational logic, which has no memory and the output depends only on the inputs, and we have another kind is sequential logic. That is a group of logic elements and it contains memory. The output will depend not only into the inputs but also depends on the value stored in memory, or it is called state in the logic block. In order to make the sequential logic works, as you can see here, we have memory, and so we will next we will talk about how the memory make and how can we make the memory work. Memory will work. We need a clock to make the memory work by sequence or by some frequency. And here we have saying about clock. We will have clock period or clock or cycle time, and we will here from here you can see it run in a way like this. From here to here it is one clock period, and we also have a clock frequency, or it is the number of cycles per second for our clock. In a clock you will have value of 0 or the low stage, and the value of 1, that is high stage. And so here you will have when the clock equal to 1 you will have the high period. When clock equal to 0 you have low period. You also have the rising edge when the clock change from 0 into 1, and you will also have the falling edge when the clock change from value 1 down to 0. During the clock period, the data transfer and computation by the combinational logic will occur, and at the rising edge or falling edge of the clock, the update for the stage will occur, or in other words, at this time the value calculated by combinational logic here will be written into memory, and so our logic will work step by step, guided by the clock, and so the memory will change to the final result. So the stage logic will work like this. We will have the first stage here, the stage get into the combinational logic, and here it work freely without clock. So value of the stage will be processed inside this and get out here when the clock change its stage, for example from low to high or at the rising edge of the clock. This value will be written back into memory, and so we have a stage element 2 available in the memory. The design will look like this. We have a stage element or some kind of memory or register. The value here get into combinational logic, and then it come back to this memory when the clock change or when the at the rising or falling edge of the clock. It depends on our design. The value of combinational logic will be written back into register and replace the old state by the new state in that memory. Saying about memory, we will need to start by DLatch. Here is the design of a DLatch. It has two input, C or the clock and D or the data. It has two AND logic and two OR logic together with three inverter. It also has two outputs, the Q or the stage and its complement Q bar. We will concentrate into Q only. This shows the graph or the work of our DLatch. DLatch will change its value, will change the outputs by the input data D when at the time that clock keeps the high period of clock. Our output for the latch, the DLatch will be changed following the value of input D. So here you can see that at the high stage of high period of clock, our Q output will equal to D. So it get high from here, and it get high when the clock change from high to low. Q still keeps the same, so nothing change in Q even if our input D change from here, but our Q will keep the same until here. And at this time you can see here the clock is high here, and so input D will take effect into output Q, and so Q change its value to the new input D from this time. The next logic is D flip-flop, in which we combine two DLatch together to make a D flip-flop, which will change the value on clock edge. Instead of clock high or low periods, it changes on clock edge. As you can see here, this DLatch will change its value, or this D value will be forwarded to this Q when clock high, and then when clock change to low, this signal will be changed to high, and so the clock here will be high, while Q here will keep the same with D here, and so when this one high, this value or the previous value of Q when clock is low will be passed through this DLatch and get from here to here and available in the Q here. In other words, we will have here I'm sorry that this latch is called master latch, and this one will be called the slave latch. And this chart show how the flip-flop work. As I said before, at the low when clock is high, here high, D from here get here. When this clock get to low, this value get to high, making this value, which is D before, get through here, and Q will, the output will be the previous D when the clock here change from high to low. So that here you can see that when clock change its value from high to low, or at the rising falling edge of the clock, value of D will be written into output Q. Similarly, at this falling edge of the clock, value of D will be written into Q here. The next we have registers, which will be group, which will be D flip-flop grouped together, many D flip-flop grouped together to make a register file. In order to make the register file work, we will need the write signal, which means that the input will be written into some register or into some D flip-flop. Inside this register file, we need two numbers, one read register number 1 and read register number 2. These two inputs will decide which register inside our register file will be read and send to the read data 1 and read data 2. For that purpose, in front of read data 1 and read data 2, we will need multiplexer to select the output of multiple registers into them. We will have the write register, or this is the register number that we will need to write into, and here we have the write data. This write data will be written into one register in register file, which is shown by the write register. When the write signal get to change from 0 to 1 or change from 1 to 0, the write operation will occur in our register file. We also have SRAM and DRAM. In fact, register or D flip-flop will be created by SRAM. It is D flip-flop is a kind of SRAM, and it is used to create a register. We also have a DRAM, dynamic RAM. SRAM is static RAM and DRAM is dynamic RAM, and so we have two kinds of RAM. SRAM or register will work much faster than DRAM, but the size of registers is very small because it is very expensive, or it takes a lot of hardware size to create SRAM. So in computer architecture, SRAM often have a small amount. For example, in our CPU, it has we have 32 registers, while the memory created by DRAM can be very big, and we can have some gigabyte of memory in our computer, but accessing to that memory will be slow, and so it is greater and far from the central processor unit. In our processor unit, you can see here SRAM will be connected with ALU to make the calculation before writing back to the memory out here created by DRAM. Next, we will go to state machines. The state machine is a sequential logic function with a set of input and output. and it also have a stage function inside, or in other words, it is a memory. And the output function will relies on current state together with the input. And of course, we will need to calculate the next stage function. We will need to calculate the next stage. In the next stage function, it is a combinational function. Here we can see an image of a state machine. We will have the current stage, or this is a memory. We can think about it as a D flip-flop, a number of D flip-flops which show the current stage of our state machine. We have a next stage function, which is a combinational logic. Output function also is a combinational logic. So the next stage function receives the current stage together with the input to calculate for the next stage, and then the next stage come back here and return back into memory or into the register and store there. While the output function takes the input of current stage together with the input, and it calculates for the output, so that the output will rely on the current state together with the input. Well, that's all about all the summarize about our lecture on computer network and architectures. Thank you very much.